Am I audible now?
Yes, sir.
Yes, sir.
Yes, okay. So let us start. So I think the screen is visible now. Are you getting the screen?
Yes, sir.
Yes, Yes, sir. sir.
So I think you might some of you might have tried different types of differential equation, and many of you might have been succeeded in solving them. So let us discuss one by one. One is a Legendre differential equation. The general form is 1 minus x square y double dash minus 2xy dash plus n into n plus 1 y is equal to 0. So here the coefficient of y double dash and y dash are variables and in terms of the variable x. Okay. So what we do while solving a differential equation having variable coefficients, we use power series solution for them. So in power series, you have to rearrange the terms in terms of y double dash plus px y dash plus qx y is equal to 0. So here, if you divide the whole expression with 1 minus x square, you will have the general form of power series. So your modified term will be y double dash plus y double dash as it is minus 2x. So y double dash minus of 2x by 1 minus x square y dash plus n into n plus 1 by 1 minus x square y is equal to 0, where your px is minus 2x by 1 minus x square and qx is n into n plus 1 by 1 minus x square. So your px and qx remain finite at x is equal to 0. So at x is equal to 0 1 ordinary point of the differential equation and it can be solved. At x tends to plus minus 1, px tends to infinite and qx tends to infinite. And your limit x tends to 0, x minus x0 px is equal to 1, where x0 is equal to plus minus 1, and limit x tends to x0, x minus x0 square qx is equal to 0, when x0 is equal to plus minus 1. So your the singular points will be x is equal to 1 and minus 1. So what do you do? So you have to solve this by using the singular points. So for that you can also use Frobenius method of extended power series to solve this, and the expression will be y is equal to summation lambda is equal to 0 to infinite a lambda x to the power k plus lambda, and your ideas is equal to summation lambda is equal to 0 to infinite a lambda k plus lambda x to the power k plus lambda minus 1, because x to the power n derivative of x to the power n is equal to n x to the power n minus 1. Here y double dash x is equal to summation lambda is equal to 0 to infinite a lambda k plus lambda into k plus lambda minus 1 multiplied by x to the power k plus lambda minus 2. So substituting this equation, you can have your 1 minus x square summation lambda is equal to 0 to infinite a lambda k plus lambda minus 1 x to the power k plus lambda minus 2 minus 2x. So summation lambda is equal to 0 to infinite a lambda k plus lambda x to the power k plus lambda minus 1 plus n into n plus 1 summation lambda is equal to 0 to infinite a lambda x to the power k plus lambda is equal to 0. So your summation lambda is equal to 0 to infinite a lambda k plus lambda into k plus lambda minus 1 x to the power k plus lambda minus 2 plus summation lambda is equal to 0 to infinite a lambda n into n plus 1 minus k plus lambda into k plus lambda minus 1 minus 2 into k plus lambda x to the power k plus lambda is equal to 0. So you have lambda is equal to minus 2 to infinite when you shift the index of summation, and you have your a lambda plus 2 k plus lambda plus 2 multiplied by k plus lambda plus 1 x to the power k plus lambda plus summation lambda is equal to 0 to infinite a lambda n into n plus lambda minus k plus lambda into k plus lambda plus 1 x to the power k plus lambda is equal to 0. So you can write it as lambda is equal to minus 2 to infinite a lambda plus 2 k plus lambda plus 2 k plus lambda plus 1 multiplied by x to the power k plus lambda plus summation lambda is equal to 0 to infinite a lambda n into n plus lambda minus k plus lambda into k plus lambda plus 1 multiplied by x to the power k plus lambda is equal to 0. So you can write an k into k minus 1 x to the power k minus 2 plus a1 k plus 1 kx to the power k minus 1 plus summation lambda is equal to 0 to infinite a lambda plus 2 into k plus lambda plus 2 multiplied by k plus lambda plus 1 plus n into n plus lambda minus k plus lambda into k plus lambda plus 1 a lambda multiplied by x to the power k plus lambda is equal to 0. So this equation is valid for all powers of x, and the coefficients of each power of x must vanish individually. So this will lead to k into k minus 1 a0 is equal to 0, and your k into k plus 1 your a1 is equal to 0. And you know the lowest power, the coefficient of lowest power forms the initial equation. So you can see the powers are like this: x to the power k minus 2, then your x to the power k minus 1, x to the power k plus lambda. So the smallest will be x to the power k minus 2. So a0 k into k plus 1 will be the initial equation, and your the largest power is x to the power k plus lambda. So n into n plus 1 minus k plus lambda into k plus lambda plus 1 multiplied by a lambda will be the recursion relation. So let us first consider the initial equation, that is k into k minus 1 a0 is equal to 0. So your k is equal to 0 or k is equal to minus 1. So let us have the recursion formula. So recursion formula will be derived from the coefficient n into n plus 1 minus k plus lambda into k plus lambda plus 1 a lambda. So from that you can have your a lambda plus 2 is equal to k plus lambda into k plus lambda plus 1 minus n into n plus 1 by k plus lambda plus 1 multiplied by k plus lambda plus 2 all multiplied by a lambda. Okay. So from the initial equation you have your k is equal to 0 or k is equal to 1, because if k into k plus 1 a0 is equal to 0. So either k is equal to 0 or k minus 1 is equal to 0 or k is equal to 1. So for case 1 your k is equal to 0. So by putting this value of k in the in the recursion relation, that is a lambda plus 2 is equal to k plus lambda into k plus lambda plus 1 minus n into n plus 1 by k plus lambda plus 1 multiplied by k plus lambda plus 2 whole multiplied by a lambda, you have your a lambda plus 2 is equal to lambda into lambda plus 1 minus n into n plus 1 divided by lambda plus 1 into lambda plus 2 whole multiplied by a lambda. So your a1 is arbitrary. So you have your a1 is equal to 0. Similarly, a3, a5, a7, so on and so forth are 0. And for lambda is equal to 0, your a2 is equal to minus n into n plus 1 by 2 factorial a0. And for lambda is equal to 2, a4 is equal to 2 minus lambda into 3 plus 2 minus n into 3 plus n divided by 3 multiplied by 4, a2 is equal to n into n minus 2 into n plus 1 into n plus 3 by 4 factorial your a2. Similarly, you have your a6 from lambda is equal to 4, and the general equation will be a2r is equal to minus 1 to the power r n into n minus 2 into n minus 4 so on so forth n minus 2r plus 2 into n plus 1 into n plus 3 into so on so forth n plus 2r minus 1 your a0 by 2r factorial. So this is for y even. So y even is equal to a0 plus a2 x square plus a4 x to the power 4 so on and so forth. And your y even can be written as your a0 into 1 minus n into n plus 1 by 2 factorial x square so on and so forth plus minus 1 to the power r n into n minus 2 into n minus 4 so on and so forth n minus 2r plus 2 into n plus 1 into n plus 3 plus so on and so forth n plus 2r minus 1 x to the power 2n by 2r factorial. So these all the terms contain odd powers of x. And in case 2 your k is equal to 1. So your a lambda plus 2 is equal to lambda plus 1 multiplied by lambda plus 2 minus n into n plus 1 by lambda plus 2 into lambda plus 3 a lambda. So your a1 is equal to 0. So you can have your a3, a5, a7 so on so forth are 0. So your for lambda is equal to 0, you have a2 is equal to minus of n minus 1 into n minus n plus 2 by 3 factorial a0. Similarly, for lambda is equal to 2, your a4 is equal to n minus 1 into n minus 3 into n plus 4 into n plus 2 divided by 5 factorial whole multiplied by a0. So the general term will be a2r is equal to minus 1 to the power r into n minus 1 into n minus 3 so on and so forth n minus 2r plus 1 so on so forth by multiplying by n plus 2 into n plus 4 by 2r plus 1 factorial. So your y odd will be a0 into x minus n minus 1 into n plus 2 by 3 factorial x cube so on so forth. And this is the solution. And the general solution of Legendre differential equation is yx is equal to a into y even plus b into y odd. Okay. So what you have done here? You have rearranged the terms in the Legendre differential equation in a general form from where we can solve it in power series. See here. And then using the power series method, that is ix is equal to summation lambda is equal to 0 to infinite a lambda x to the power k plus lambda. You have your y dash and y double dash. Then by putting it in the equation, you have the indicial equation and you have the recurrence relation. From the indicial equation, you know the roots, that singularities, that is the value of k and for Legendre differential equation k is either 0 or 1, and by putting it in the recursion relation you have the solution. Similar case will be for the other differential equations. So let us have another one, that is your Hermite differential equation. So the general form of Hermite differential equation, please say what is it? Y double dash minus 2xy dash plus 2 alpha y is equal to 0. So here your px is equal to minus 2x and qx is equal to 2 alpha. So by solving it in power series, you have to make take y is equal to summation lambda is equal to 0 to infinite a lambda x to the power lambda. So you can see that y dash is equal to y dash is equal to your summation lambda is equal to 0 to infinite a lambda k plus lambda multiplied by x to the power k plus lambda minus 1, and y double dash is equal to lambda is equal to 0 to infinite a lambda k plus lambda into k plus lambda minus 1 multiplied by x to the power k plus lambda minus 2. And by substituting it in the original equation, you have your indicial equation and your recurrence relation. So the indicial equation will be what? The indicial equation will be your k into k plus 1 a0 is equal to 0. So your k is equal to 0 or 1, and your recurrence relation will be the coefficient of highest power of x. So that is a lambda plus 2 which is equal to 2 into k plus lambda minus alpha divided by k plus lambda plus 1 multiplied by k plus lambda plus 2 a lambda. So for k is equal to 0, you have your a lambda plus 2 is equal to 2 into lambda minus alpha divided by lambda plus 1 into lambda plus 2 a lambda. And your for lambda is equal to 0, your a2 is equal to 2 minus alpha by 2 factorial whole multiplied by a0. And for lambda is equal to 2, your a4 is equal to 2 square multiplied by minus alpha multiplied by 2 minus alpha multiplied by a0 by 4 factorial and so on and so forth. And the general term will be a2j is equal to minus 2 to the power j alpha into alpha minus 2 into alpha minus 4 so on and so forth alpha minus 2j plus 2 divided by 2j factorial. And you can have your y even, which is nothing but a0 into 1 plus 2 minus alpha by 2 factorial x square plus 2 square multiplied by alpha into 2 minus alpha by 4 factorial x to the power 4. And for case 2, where k is equal to 1, your a lambda plus 2 is equal to 2 into lambda plus 1 minus alpha a lambda by lambda plus 2 into lambda plus 3, and you have your a2 by putting lambda is equal to 0, and a2 will be minus 2 into alpha minus 1 by 3 factorial whole multiplied by a0. Similarly, you have your a4 by putting lambda is equal to 2 and a6 by putting lambda is equal to 4, and the general term is a2r is equal to minus 2 to the power r alpha minus 1 into alpha minus 3 into so on and so forth alpha minus 2r plus 1 divided by 2r plus 1 factorial. Okay, so this is the solution. Similarly, you can have your Bessel's differential equation and you can solve it by power series. The general form of your Bessel's differential equation will be, anybody, x square d square y by dx square plus x dy by dx plus x square minus p square y is equal to 0. So we have to divide the expression by x square to convert it in a form which can be solved in power series, and you have your d square y by dx square plus 1 by x dy by dx plus x square minus p square by x square y is equal to 0, where your px is equal to 1 by x and qx is equal to x square minus p square by x square. So the solution can be found out from the power series method, and your ix can be taken as summation lambda is equal to 0 to infinite a lambda x to the power lambda plus k, and your y dash will be summation lambda is equal to 0 to infinite a lambda multiplied by lambda plus k multiplied by x to the power lambda plus k minus 1, and your y double dash is equal to summation lambda is equal to 0 to infinite a lambda plus k multiplied by lambda plus k minus 1 multiplied by x into lambda plus k minus 2 so on and so forth. And by putting this in the original equation, you have your initial equation as well as the recurrence relation. So what you have, your from initial equation you have your k is equal to plus p or plus p, because the initial equation is the lowest power of the expression, and your initial equation is a0 k square minus p square is equal to 0. So since a0 is not equal to 0, k square minus p square is equal to 0, so k is equal to plus minus p. So for, and the recurrence relation will be the coefficient of highest power of lambda, highest power of x, that is x to the power k plus lambda. So the coefficient is your summation lambda is equal to 2 to infinite a lambda into k plus lambda minus 1 plus k plus lambda minus p square plus a lambda minus 2. So this will be 0, and from that you can have your a lambda plus 2 is equal to minus a lambda multiplied by 1 by k plus lambda plus 2 square minus p square. And from by putting the value of k is equal to p, you can have your case 1, and your a lambda plus 2 is equal to minus lambda multiplied by 1 by 2p plus lambda plus 2 whole multiplied by lambda plus 2. And from that you have your a2 a4 so on so forth, and general expression is a2n is equal to minus 1 to the power n a0 p factorial by 2 to the power 2n n factorial p plus n factorial. And your the solution of Bessel equation for k is equal to plus p is y plus is equal to a0 x to the power p 1 minus p factorial by 2 by 2 square 2 to the power 2 square 1 factorial multiplied by p plus 1 factorial whole multiplied by x square plus p factorial by 2 to the power 4 multiplied by 2 factorial multiplied by p plus 2 factorial whole multiplied by x to the power 4, and the general expression will be a0 p factorial 2 to the power p summation n is equal to 0 to infinite minus 1 to the power n 1 by n factorial multiplied by n plus p factorial whole multiplied by x by 2 to the power 2n plus p. And you have your jpx is equal to summation n is equal to 0 to infinite minus 1 to the power n 1 by n factorial into n plus p factorial whole multiplied by x by 2 to the power 2n plus p is equal to summation n is equal to 0 to infinite minus 1 to the power n whole multiplied by 1 by root over of n plus 1 multiplied by n plus p plus 1, and your jpx is called Bessel's functions for of first kind and having order p. And if you take k is equal to minus p, then you have Bessel's equation of second kind, that is j minus p, and this is nothing but summation n is equal to 0 to infinite minus 1 to the power n multiplied by 1 by n factorial whole multiplied by n plus p factorial whole multiplied by x by 2 to the power 2n minus p. Okay, so you can have your j minus p is equal to minus 1 to the power p jp. Okay, and starting from and you have your Bessel's function. So this is in general you can have an idea how to solve differential equation. So you have to first convert it in such a form. You can use the power series or Frobenius method. Then you have to have your y term, y dash term and y double dash term, put it in the original equation. Then your initial equation from which you have the roots or singular points, that is k value. Then different cases for different k values, and by putting the value of k in the recurrence relation, which is nothing but the coefficient of the highest power of x, you have your solution. Am I audible? Am I audible?
Yes, sir.
Not audible?
Yes.
Yes, sir, audible.
Okay. So next there are some other things which you need to know so far as differential equation is concerned. Okay. So now after getting the solution, so let us have the Legendre differential equation. So you have the solution which I have discussed now. Then Legendre polynomial. So consider the power series represented by the equation that represents the solution of the Legendre differential equation. Then the ratio of successive terms of the power series will be n minus 2r plus 2 into n plus 2r plus minus 1 by 2r into 2r minus 1 whole multiplied by x square and its modulus. This implies that the series converges for modulus of x smaller than 1 and diverges for modulus of x greater than 1. It can also be shown that the series converges for x is equal to plus minus 1. So similar conclusion can be drawn for the series represented by our x equation. We may obtain a single series in descending power of x valid for both even and odd n. So your n will be n plus 1 into n plus 2 by n minus lambda. Your n is equal to lambda plus 1 into lambda plus 2 divided by lambda minus n into lambda plus n plus 1 whole multiplied by a lambda plus 2. And the general, from the general term you have your required solution, that is ix is equal to n summation r is equal to 0 to n minus 1 to the power r n factorial square multiplied by 2n minus 2r factorial by r factorial 2n factorial n minus r factorial n minus 2r factorial whole multiplied by x to the power n minus 2r, where your n is equal to n by 2 if n is even and n minus 1 by 2 if n is odd. So your ix can be written as pnx, where pnx are called the Legendre polynomial of first kind. So you can evaluate different values of pn for p0 to find out to evaluate p0x. You have to put 0 in place of n in equation 3.48. So you will have p0 x is equal to minus 1 to the power 0 into 0 factorial, because 2n minus 2r will be 0. Then 2 to the power n is equal to 2 to the power 0. Then 0 factorial, 0 factorial, 0 factorial, whole multiplied by x to the power 0 is equal to 1. So p0 x is equal to 1. Similarly, p1 x you can find out by putting n is equal to 1 and its value is x. So similarly your p2 x is evaluated by putting the value n is equal to 2, and the value is p2x is your 1 minus 2 3x square minus 1. Similarly p3x will be half multiplied by 5x cube minus 3x. Similarly p4, p5 and p6 are shown in the screen. So you can plot p0 and p1 in a graphical form as shown in the screen, which are linear straight lines. And if you plot p2, p3, p4 and p5, it will look like as shown in the screen. Okay. Similarly, like the Legendre polynomial, you can have your Hermite polynomial. So how can you find out the Hermite polynomial? See, your y odd, which I was discussed earlier today, is a0 x minus 2 into alpha minus 1 3 factorial into x cube plus 2 into alpha minus 1 into alpha minus 3 by 5 factorial x to the power 5, so on and so forth. So your yx is a y even plus b y odd. So your y even is equal to an expression, and y odd is another expression. And Hermite differential equation converges for all finite values of x. Am I audible?
Yes, sir.
Am I audible? I think I am not audible.
Yes, sir.
Yes, sir. Yes, sir.
Am I audible?
Yes, sir.
Am I audible?
Yes, sir.
Yes, sir.
Okay. Is the screen visible?
Yes, sir.
Yes, sir. Visible, sir.
Is the
Yes,
sound is
sir.
clear now or previously it was more clear?
Yes, sir.
Okay. So you for a Hermite polynomial, you have your n even and n odd, and Hermite differential equation converges for all finite values of x. So if the parameter alpha of the differential equation is a non-degenerate integer, then depending on whether it is even or odd, one of the above solution discussed now terminates after a finite number of terms and reduces to a polynomial. So if alpha is equal to even, you have your y even is equal to 1 minus 2 into 4 by 2 factorial multiplied by x square plus 2 square multiplied by 4 into 4 minus 2 by 4 factorial to the multiplied by x to the power 4, and this is the polynomial of degree 4. And for alpha is equal to odd, and say n, your y odd is equal to x minus 2 into 5 minus 1 by 3 factorial x square plus 2 to 2 square 5 minus 1 into 5 minus 3 by 5 factorial all multiplied by x to the power 5, and it is a polynomial of degree 5. So your this polynomial solution of Hermite differential equation can be represented as polynomials of degree n. So your yn is equal to a0 plus a2 square plus so on and so forth, and yn is equal to a1 plus a3 q plus so on and so forth, even and odd. So you have your a lambda is equal to minus lambda plus 1 into lambda plus 2 by 2 into n minus lambda whole multiplied by a lambda plus 2. So you have your a n minus 2, a n minus 4, a n minus 6 and similar terms. So you can have your yn is equal to hn, which is the Hermite polynomial, and its expression will be summation j is equal to 0 to n minus 1 to the power j multiplied by n factorial multiplied by 2x to the power n minus 2j by j factorial into n minus 2j factorial. So this Hermite polynomial is of degree n, and you can evaluate h0, h1, h2 by putting n is equal to 0, 1, 2 respectively. So your h0 will be minus 1 to the power 0, 0 factorial, 2x to the power 0 divided by 0 factorial into 0 factorial is equal to 1. Similarly, your h1 is equal to minus 1 to the power 0 into 1 factorial multiplied by 2x to the power 1 by 0 factorial into 1 factorial is equal to 2x. Similarly, your h2x is equal to 4x square minus 2, and h3x is equal to 8x cube minus 12x. So this can be presented in a graphical form. Your H1 is a increasingly linear curve, a straight line. H0 is also a straight line, but H2 is a non-linear curve. Okay, so this is all about your polynomial. Similarly, you have polynomials for other differential when you solve other differential equation. Then the next thing is your Rodrigo formula for Legendre polynomial. The Rodrigo formula for Legendre polynomial can be obtained and it is a series form. Your Pnx is equal to summation r is equal to 0 to n factorial n 0 to n star minus 1 to the power r multiplied by 2n minus 2r factorial by 2 to the power n into r factorial into n minus r factorial into n minus 2r factorial whole multiplied by x to the power n minus 2r. And Rodrigo formula will be Pn is equal to 1 by 2 to the power n by n factorial d to the power n x square minus 1 to the power n by dx to the power n. And the solution, the derivation or the proof is shown in the screen. And this Rodrigo formula for Legendre polynomial can be used to evaluate Legendre polynomials P0, P1, P2, P3, P4, etc. by putting the values of n in the expression. Similarly, you can have Rodrigo formula for Hermite polynomial and other polynomials also. Let us have it. Here, see. For Hermite polynomial, which the Rodrigo formula can be written as hnx is equal to minus 1 to the power n ex square del to the power n e minus x square by del x to the power n, and the proof is shown in the screen. And from this hn, you can have your h0, h1, h2, h3, and other polynomial expressions. So for all others, associated Legendre, Laguerre, Bessel's, okay, you have your Rodrigo formula. And from that you can have your polynomials. Then you have integral representation of Legendre polynomial, which is shown in the screen. There are two types of integral representation. One is the Shapley integral representation, and other is Laplace integral representation. So the first one is P and Z is equal to is equal to 2 to the power minus n by 2 pi I integration over the closed contour t square minus 1 to the power n by t minus z to the power n plus 1 dt, and your Laplace integral representation will be P and Z is equal to 1 by pi integration 0 to pi z plus root over of z square minus 1 cos phi to the power n d phi. Generating function for Legendre polynomial, your g, which is a function of t comma z, is equal to summation n is equal to 0 to infinity to the power n p and z. And the derivation is shown in the screen. And it can also be written as 1 minus 2tx plus t square to the power minus half. And for Hermite polynomial, you can see the generative function is gx comma t is equal to e to the power 2xt minus t square, and it is an important expression, and the proof is shown in the screen. Then another important thing is recurrence relation. And which are usually asked in different examinations as 5-mark question or 8-mark question. So there are recurrence relation among the gender polynomials. One is 2n plus 1x, pnx is equal to n plus 1, pn plus 1x plus pn minus 1x, and the proof is shown in the screen. And the second recurrence relation will be pn plus 1 dash plus pn minus 1 dash is equal to 2x pn dash plus pn. This is the second recurrence relation, and the proof is shown in the screen. Similarly, you have your 2n plus 1 pnx is equal to pn plus 1 dash plus p dash, and your pn plus 1 dash is equal to x pn dash plus n plus 1 pn, and your pn minus 1 dash is equal to x into pn dash minus n into pn. As 1 minus x square pn dash is equal to n into pn minus 1 minus n plus nx pn. Okay. Similarly, you have recurrence relation in Hermite polynomial and other polynomials also. See here for Hermite polynomial, which is derived from the Rodrigo equation, you have your hn plus 1 minus 2x hn plus 2n hn minus 1 is equal to 0, and your hn dash is equal to 2n hn minus 1, and hn double dash is equal to 2n hn minus 1 dash. Okay. Then your orthonormality and orthogonality condition for Legendre, Hermite, Bessel's, associated Legendre, Laguri, and other polynomials. And the proof is shown in the screen for a Legendre polynomial. Your IMN is equal to integration minus 1 to 1 PM x Pn x dx. Similarly, orthogonality condition, the proof is shown in the screen. Your n into n plus 1 minus m into n plus 1 integration minus 1 to 1 pn pm dx is equal to 0. And for a Legendre, we have orthonormalization, that is integration minus infinite to infinite e to the power minus x square hnx hmx dx is equal to 0. This is the orthogonality condition, and orthonormality condition is your integration minus infinite to infinite e to the power minus x square by 2 hnx into e to the power minus x square by 2 hmx dx is equal to root over pi 2 to the power n factorial del nm n comma m. Are you getting it?
Yes, sir.
Am I audible? So see, am I audible?
Yes, sir.
So see, here your Bessel's function,
Yes, sir.
which I was discussing, your solution, and these are the Bessel's function J1, J0, and J2. Then your recurrence relation, which I was discussing. Then your generating function g is equal to exponential x by 2, t minus 1 by t, summation n is equal to minus infinite to infinite j n t to the power n, and your some worked out examples. And this is the Bessel equation of second kind, which is called as Weber function.